Welcome to our problem set covering topics of torque and angular momentum. This first problem has a disc-shaped platform which has a known moment of inertia, I sub d. The platform is mounted on a fixed axle and rotates in a horizontal plane with an initial angular velocity omega sub d. The motion is counterclockwise. Now, after an unknown time interval, the disc comes to rest. A single point on the disc revolves around the center axle hundreds of times before the disc comes to rest. Frictional forces are considered to be constant. A student must determine the angular impulse that frictional forces exert on the disc from the moment it rotates with angular velocity in the counterclockwise direction until it stops. What additional data, if any, should a student collect to determine the angular impulse on the disc? Justify your selection. All right, great. So the student is trying to find the angular impulse, or in other words, the change in angular momentum that this disc experiences from the time that we first start measuring to the time that it comes to rest. So what that means is we're told that we know the moment of inertia, and we also know the initial and final velocity. The initial is omega sub d, the final velocity is 0. So is that enough to find out what the impulse is without needing to take any more data? Because usually that's the first thing you should ask when it's asking what more information, if any, is needed. It's a good chance that no more information is needed, but we need to see if we can actually find the impulse from what we have. Well, impulse, let me use my pen. Impulse is just a change in momentum. And we can define change in momentum as, well, if momentum itself is just moment of inertia times angular velocity, then we can say that impulse or change in momentum is equal to moment of inertia times final angular velocity minus moment of inertia times initial angular velocity, which we're saying is omega sub d, not b, d. All right. So this could be an expression or an equation for the impulse or the change in angular momentum. That said, we have everything here. We know everything here. We know that omega sub d is the initial. We know that omega sub f is 0 because it comes to rest. And then it says that the moment of inertia is known. So actually no other information is required in order to find the impulse or the change in momentum. So I'm going to go ahead and click D and move on. All right, in this problem, we have the same setup. So this portion of the setup is the exact same as last time. In fact, this is almost the same, but we'll go ahead and read this paragraph. A student must determine the angular impulse that frictional forces exert on the disc from the moment it rotates with angular velocity in the counterclockwise direction until it stops. Which of the following could the student have used in order to approximate the initial angular velocity of the rotating disc? All right, let's go through each one of these so that we understand how they work actually. A says a motion sensor to collect data about the disc's linear position as a function of time after the disc was set into motion. That's great, but in order to get the angular velocity, we're going to have to use a procedure that allows us to collect information about the angular position. In other words, the amount of radians it is traveling. So the linear position is not necessarily going to tell us that. For B, it says a motion sensor to collect data about the disk's angular position as a function of time after the disk was set into motion. And you might think, okay, well, now this one will help us, but a motion sensor alone is really only capable of registering linear changes in an object's position. It doesn't really give you data on angular position as it changes, because from its perspective, you're kind of just moving back and forth. All right. It doesn't tell you really anything about the angular position of a circle, because that back and forth motion could be different amounts of radians depending on radius and everything like that. A motion sensor is really not adequate for measuring angular position. For C, it says a slow motion camera that films the disc to determine the amount of time it took a particular point on the disc to make its first revolution after the disc was set into motion. This is actually good because we have information that essentially the disc rotated hundreds of times. And so the reason why I think C is not perfect, but still pretty good, is because that first rotation is going to represent such a small amount of time in which the disc was rotating that it's almost like it's a close enough value. The average velocity in that first revolution is close enough to the initial velocity to basically be an approximation of the initial velocity. And that's kind of what we're looking for here, just an approximation in the first place. It says it here, an approximation of the initial angular velocity. So I do like C, and a slow motion camera would help us see how long it took that first revolution, which we would know that first revolution represents 2 pi radians, and then we'd have the time so we could find the velocity, or at least the average velocity of that first revolution. For D, we have a stopwatch to determine the amount of time it took a particular point on the disk to make all of its revolutions from the instant in time when the disk was set into motion to the instant in time when the disk came to rest. Now, you could technically do this with a stopwatch if you were really quick, which first off, that's not going to be nearly as good as a slow motion camera. But also the specific procedure in answer choice D would give you the average velocity over the course of the entire motion of the disk from the time that it starts to the time that it comes to rest. So that's not going to be a good approximation of the initial velocity like C was. All right. So none of these answer choice actually give you the exact initial velocity, but C does give you the closest approximation to that initial angular velocity. So we're going to circle that and move on. In this question, we have a bit of a math problem. We have a lever arm here, which has its axis of rotation on this black circle, and there are 4 forces acting perpendicular to the lever arm. So good, at least we don't have to deal with trigonometry. The figure above represents a stick of uniform density that is attached to a pivot at the right end and has equally spaced marks along its length. Any one or a combination of the 4 forces shown can be exerted on the stick as indicated. If all 4 forces are exerted on the stick, which was initially at rest, that's important. What is the angular momentum of the stick after 2 seconds? Okay, so because it's initially at rest, we can actually use the impulse-torque relation here, because we know that the change in angular momentum is going to be equal to the final angular momentum, because it started at 0. That said, the force, or I keep on saying force, but it's the torque angular impulse relation, is just this. Change in angular momentum is equal to torque times change in t. So we know time. It's going to be 2 seconds. We have enough information to find torque, but we're going to have to do a couple of calculations. All right. So those calculations are just that torque is equal to R times F, perpendicular, which all of our forces are perpendicular, so we don't have to deal with any trigonometry here. And so all we have to do is take each force and multiply it by how far it is from the axis of rotation. And then from there, we just need to add them all together, and that will give us our net torque. Net torque is what we're going to plug into our torque impulse relation. So for F1, we're going to call that torque 1. That's going to be equal to 0.5, because it's 0.5 meters from the axis of rotation, times 200 newtons. All right, that's clearly going to give us 100 Newton meters, and that's good. So we know that one. I'm going to call the downward torques, or the counterclockwise torques, positive. And I'm going to call the upward torques, or the clockwise torques, negative. So that means torque 1 and torque 2 are going to be positive, whereas torque 3 and torque 4 are going to be negative. It doesn't really matter which is which, as long as they're consistent with what direction they're pointing. All right. So torque 2 is going to be equal to, this should be a whole meter times 100 newtons. So not much math to be done there. That's just going to be 100 Newton meters. 1 times 100 is 100. All right. For torque 3, we have 1.5 meters times 50. Okay, so if we multiply 50 by 1.5, we get 75 Newton meters. And so we're going to call this negative, because it's in the opposite direction of 1 and 2. So then torque 3 is going to be equal to 2, because it's 2 meters away from the axis of rotation, times 25 newtons, which is going to be equal to 50, and that's negative 50 Newton meters. Good. So if we go ahead and just add these together, we have 200 minus 75 minus 50. So 200 minus 75 is 125, minus 50 is 75. So we end up with a positive 75 Newton meter net torque. All right. So this is our net torque, our torque net. It's the sum of all the torques acting on this lever arm. Good. Now that we know that, we can just multiply that by our time, because we're going to plug this 75 into our torque impulse relation, multiply it by our time, which is 2 seconds. 75 times 2 is just 150. That's going to be our change in momentum. And we said at the beginning of this problem that the change in momentum is going to be equal to our final momentum, because we started at 0. So I'm going to go ahead and circle A, because 75 times 2 is 150, and we're done. In this problem, we have the same setup, the same lever arm with the same forces acting on it. And the question is, which of the four forces, when exerted alone, will change the angular momentum of the stick at the smallest rate? This is just saying which of the four forces generates the smallest amount of torque. That said, we just calculated those in the torques that each one generated in the previous problem. I'll copy it here. And so we can see that the torque with the smallest magnitude is actually T sub 4 with a 50 Newton meter magnitude of torque generated. So we're going to go ahead and say that the fourth force, this small 25 Newton force, is going to generate the smallest torque, which will in turn generate the smallest angular momentum, or the smallest change in angular momentum over the course of our 2-second period from the previous problem. In this problem, we have an axle that passes through a pulley. Each end of the axle has a string that is tied to a support. You've probably seen this figure in the previous problem set if you've gone through that one. A third string is looped many times around the edge of the pulley, and the free end is attached to a block of mass m sub b. The block is held at rest initially, but when the block is released, the block falls downward, clearly under the force due to gravity. Consider the clockwise to be the positive direction of rotation, because that's the direction that this wheel is going to spin after that mass sub b is let go. Frictional effects from the axle are going to be negligible here, and the string wrapped around the disc is never going to fully unwind. We know that the rotational inertia of the pulley is going to be 1/2 mr squared, and it's going to be about its center. So the radius of this wheel is going to be our distance from the axis of rotation. The block falls for some time T sub naught, but the string does not completely unwind. What is the change in angular momentum of the pulley block system from the instant that the block is released until time 0? Okay. So we need to find the impulse. So change in angular momentum. So what comes to mind initially is the impulse torque relation. Delta L is equal to net torque times delta T times our change in time. All right. So my initial question here is, do we have enough information to make an expression equal to delta T? Because that looks like what it's probably going to be looking for, because I even see our time at the end of some of these answer choices, and it makes me think that, yeah, we're going to just use this, but we're going to substitute some expression for torque. That said, torque is equal to, all right, alone it's equal to R times the force that is perpendicular to the lever arm. And in the case of an actual spinning wheel, the lever arm is the whole thing. So any force that's tangent to that spinning wheel is going to be considered a perpendicular force. Luckily, when we have a string wrapped around and a tension in the string that's actually unwinding, then that's always going to be a tangent force. What I mean is this force here is definitely tangent downward. And this force is actually due to the force due to gravity. So that force is going to be m sub b times acceleration due to gravity. So we know what the force is, and it's tangent, so we can say it's perpendicular, so we don't need any trigonometry. So that said, I can say that if R is capital, if the radius or the distance from the axis of rotation is capital R, then I can say the torque here is going to be equal to R times m sub b g, g being acceleration due to gravity. So if I take that and I go ahead and plug it in for my impulse torque relation, then I know that my change in momentum is equal to R m sub b times the acceleration due to gravity times delta T, which in our case delta T is just T sub naught. Looks like we have an answer choice that looks just like that. Very nice. Let's move on. So here we have a problem where we have a rod of length 1/2 meter that's placed on a surface. One end of the rod is connected to a pivot that will allow the rod to rotate around the pivot without frictional forces. A lump of clay is launched toward the free end of the rod at a known speed. So we know the velocity of the lump of clay. When the lump of clay strikes the free end of the rod, it sticks to the rod. Okay, the equation for the rotational inertia of the rod about its pivot is 1/3 ml squared, capital M being the mass, L being the length of the rod. Which of the following quantities, when used together, could a student measure in order to determine the change in angular momentum of the rod from when it was initially at rest to the instant in time when the rod has rotated 90 degrees in the counterclockwise direction? All right, so our answer choices here are the mass of the lump of clay, the mass of the rod, the tangential speed of the end of the rod as it is after it has rotated 90 degrees in the counterclockwise direction, and the time it takes the rod to rotate 90 degrees in the counterclockwise direction. So this is actually a pretty tough question. So let's break down which two are the correct choices. Because what we need to do is we need to basically look for finding the change in angular momentum. So because the initial momentum is 0, the initial angular momentum of the rod is 0, we can say that the final angular momentum is the change in angular momentum. So that makes it a little bit easier because all I need to find is just the final angular momentum. So I know that the mathematical definition for angular momentum is moment of inertia times angular velocity. And again, we're looking for final here. So we need some information about the final point, or in this case, when the rod has rotated 90 degrees in the counterclockwise direction, right? So what we need, what would be nice is if we just had the angular velocity at the 90-degree point, all right? But there's not actually any of the answer choices that give us the angular velocity. But another thing that we're definitely going to need is definitely going to need the mass of the rod, because in order to actually calculate this, we need to plug in the mass of the rod in for our expression for moment of inertia. What I mean is that I actually is 1/3 ml squared. All right, and we know the length of the rod is 0.5, so we don't need that. But we do know we do need to know the mass of the rod in order to fully calculate this. And so we'd be multiplying all this by the final velocity. Now, the tricky part is that the only other one that's going to give us the missing piece that we're missing, which is the final velocity, is actually c, and I'm going to explain to you why. It's not angular velocity, so you can't just assume that that's angular velocity. It's tangential velocity, which is going to be our linear velocity. But if you have linear velocity and you have the radius from your axis of rotation, then you have angular velocity, because you have to remember that omega is equal to v over r. All right. So yeah, we know what the radius is because we know that we're talking about the tangential speed at the end of the rod. So the radius is going to be equal to L. So then what we can do is we can say that L final, or in other words, our change in momentum, is going to be equal to 1/3. We're going to take the mass of the rod times the length squared of the rod times the final velocity, which is what c is going to give us, over L, which is going to be the length of the rod or the radius from the axis of rotation. So B and C are what we're going to need in order to find this final angular momentum, which, like I said before, is going to be equal to our change in angular momentum. Let's move on. In this problem, we have two figures, each one representing a different experiment. It says, two small objects of mass m0 and a rotating platform of radius r with known rotational inertia about its center compose a single system. Students use the system to conduct two experiments. The objects are assumed to be point masses. Good, so it looks like in experiment 1, each object of mass m0 is placed a distance r1 away from the center of the platform, such that both masses are on opposite sides of the platform. A constant tangential force F0 is applied to the edge of the platform for a time delta T0, as shown in figure 1. All right, so that's everything we just read is discussing this setup for experiment 1. The system was initially at rest, so it initially had no velocity or momentum or anything like that. Then for experiment 2 in figure 2, each object of mass m0 is placed a distance r2 away from the center of the platform, such that both masses are on opposite sides of the platform. Now in experiment 2, r2, the distances that the objects are, the point masses, are from the axis of rotation, are less than in experiment 1. So r2 is less than r1. A constant tangential force F0, the same F0 as in experiment 1, is applied to the edge of the platform for the same amount of time at delta T0, as shown in figure 2. The system was also initially at rest. Okay, good. So we know that there's a tangential force, the same tangential force applied to both experiments for the same amount of time. The only difference is that experiment 2 has our masses closer to our axis of rotation than experiment 1. And I'll tell you what that will change about the two objects is it'll make the moment of inertia for experiment 2 smaller than the moment of inertia for experiment 1. All right, because the moment of inertia is kind of defined as how closely packed the masses of an object that's rotating are to the axis of rotation. So the masses in experiment 2 are closer to the axis of rotation, so it's going to have a smaller moment of inertia. Great. Now, let's see what the question says. Consider both experiments, figure 1 and figure 2. How do the angular momentum of each system and the angular speed of each system compare after delta T0? Okay, so using delta T0 and knowing that first we're looking for the angular momentum, or in other words, the change in angular momentum, we can say that the change in angular momentum, based off of the impulse-torque relation, change in angular momentum will be equal to the torque, the net torque generated, the net external torque, times delta t. So this torque should actually look a little bit more like lowercase tau. So let's call it that. And then so delta t. So this is the relationship we're dealing with here. Now, the force applied to the edge of the disk is the same in both experiments, and the disk is the same in both experiments. So torque is going to be the same in both experiments, and delta t is going to be the same in both experiments. So regardless of where the masses are, we know that they're going to have the same change in momentum. All right, so I'm going to cross out C and D because they're suggesting that we have different angular momentums. That just won't be true because the angular momentum, the change in angular momentum over some period of time, doesn't actually care about what the moment of inertia of the disk is. It's just the torque times the time that the torque was applied. So we're going to have either A or B. So let's decide what the difference between A and B is. A says that our final velocity, final angular speed of experiment 1 will be greater than the final angular speed of experiment 2. And B says the opposite, that the final angular speed of experiment 1 will be less than the final angular speed of experiment 2. All right, let's see about that. We know that angular velocity, let's see, angular velocity, we can call it torque is equal to moment of inertia times change in angular velocity over change in time. All right, I went ahead and used this relationship because we know moment of inertia, we know change in time, and assuming we can figure out force, we know what torque is. All right, so the question is, if we solve for change in angular velocity here, it'll look something like this, where we have torque times delta t over moment of inertia, sorry, that should be an I, over moment of inertia is equal to change in angular velocity. And because the initial angular velocity is 0, the final angular velocity is equal to the change in angular velocity. I use that kind of logic in a lot of problems here. And the question is, the only thing that's really different between these two experiments is the fact that experiment 2 has a smaller moment of inertia than experiment 1. So if we lower our moment of inertia, as you can see, it's at the bottom of a ratio set equal to our change in angular velocity, then that means we're going to increase our angular velocity. So given the same torque and the same time, lowering moment of inertia increases what the final angular velocity is going to be. So that tells me that the angular velocity for experiment 2 is going to be higher after our time period than the angular velocity in experiment 1. So I'm going to go ahead and choose B because that says that angular velocity of experiment 1 is less than angular velocity of experiment 2, and that's exactly what we're saying.
Here we have a motor that rotates an axle that is connected to one end of a rod, as shown in the figure above. Students may adjust the speed at which the motor causes the axle and rod to rotate. During an experiment, what essential quantity or quantities should be measured or determined in order for the students to determine the rod's change in angular momentum after 8 seconds? Justify your selection. All right, so with this problem, before I even look at the answer choices, I'm going to write down the force or the torque impulse relation, as I call it. That's going to be change in angular momentum is equal to torque times time. All right, so we're given time and we want angular momentum. So my initial reaction is to say, well, if we could measure torque, that'd be great. And it looks like there is an answer choice that does say the average net torque applied to the rod. But let me see if any of these other answer choices would be more correct. Let me look. The mass of the rod, the length of the rod, the average net force applied to the rod. Okay, so not D, because if we're measuring the average net force applied to the rod, we're basically measuring the average net torque, and we need torque. Torque is more related to angular velocity, or it's more related to impulse and angular velocity than force. But then for mass and length, the question is why would mass be enough? Would length be enough? And I think the answer to that is that if we wanted to calculate the impulse or the change in angular momentum without torque, then we'd have to write impulse as, I'd have to break torque up into me see, moment of inertia times angular acceleration times delta S. And we don't have enough information to find moment of inertia with just the mass or just the length of the rod. We would definitely need both of them to do that. So A or B alone don't actually answer the question for me, so I'm going to go with C. All right, so in this problem, we have a torque versus time graph. And as I've said many times, anytime you have a torque versus time graph or a force versus time graph, you're going to be talking about change in momentum because the area underneath the curve is change in momentum. So this question says, a horizontal disc of radius 0.2 meters and mass 0.3 kilograms is mounted on a central vertical axle so that a student can study the relationship between net torque and change in angular momentum of the disc. In the experiment, the student uses a force probe to collect data pertaining to the net torque exerted on the edge of the disc as a function of time, as shown in the graph. The disc is initially at rest. At what instant in time does the disc have the greatest angular momentum? All right, so as this graph is going from time 0 to time 1 second, all the way to time 2 seconds, and then to 2.5, this entire time that it's going, the area underneath the curve is increasing. Even as the slope of this graph starts to decrease, the total area is still increasing. And remember, the area is what is defined as the angular momentum. So the point in which we have the greatest angular momentum is going to be the end of the graph, assuming that we never cross to the other side of the horizontal axis. All right. And we never do here. We never have any negative torque. So we're just going to go ahead and just say the end of the graph. That end of the graph point, it says 2.5 seconds. All right. 2.5 seconds. So here we have a rod that represents a lever arm with its pivot shown and a graph of its angular acceleration with respect to time. The question says, a rod is at rest on a flat horizontal surface. One end of the rod is attached to a pivot, and the rod may freely rotate around the pivot if acted on by a net external torque. In an experiment, the rod is initially at rest, and the student exerts a net torque on the rod. Data are collected to create a graph of the rod's angular acceleration as a function of time. Friction forces are considered to be negligible. How can the student use the graph to determine the angular momentum of the rod at 5 seconds? All right, so now angular acceleration and time don't immediately give you impulse or change in angular momentum right off the bat. So let's see what we can do. So when you're looking at a graph, you can kind of do two things. You can either take the slope of the graph or you can take the area underneath the graph. Usually those two things represent something. If we're talking about acceleration and time, then if we want to take the area underneath the graph, that's kind of like multiplying them together, okay? If we want to take the slope, that's kind of like taking their quotient, all right? That said, which one of these two options will help us to get impulse? Well, if we think about the force-impulse relation, if I think about the force-impulse relation, or in this case, the torque-impulse relation, then that tells me that torque is equal to, or actually, let's go ahead and write it as delta L. Delta L, angular impulse, is equal to torque times time, okay? That's torque times time. Now, of course, that's delta time. Now, there's acceleration. We can break up torque in terms of acceleration if we want to, angular acceleration. We could say that impulse is equal to, and then according to Newton's second law, torque can be equal to moment of inertia times angular acceleration. So I could say that I can plug this in for torque and say that impulse is equal to moment of inertia times angular acceleration times delta t. So over here, I said, if we're finding the area underneath this curve, it's kind of like taking acceleration and multiplying it by delta t. That said, if we do that, we have everything we have in this equation except for I, so we're just missing a factor of I. So let's see if knowing that information gives us the right answer. Option A says determine the average angular acceleration from 0 to 5. Nope. B says determine the area bound by the curve and multiply it by the inertia of the rod. That's exactly what this equation is saying. In this problem, we have two figures. We're seeing the side view of a pulley and then a graph that looks like a little bit different than most graphs that we've probably dealt with. We have distance fallen for this mass plotted on the y-axis, and then we have the time that takes, but not just time, it's the square of time, so it's time squared. The question says, one end of a string is attached to a 0.1 kilogram object. The string is wrapped around a pulley of known rotational inertia. Good, so we know the rotational inertia. That's one thing to keep in the back pocket. And a radius of 0.5 meters. The central axis is supported by the strings that are connected to the ceiling, as shown in figure 1. In an experiment, the 0.1 kilogram object is released from rest, and the necessary data are collected to graph the distance fallen by the object as a function of the square of time fallen, as shown in figure 2. A student makes the following claim, and the claim is here. Figure 1 and figure 2 can be used to determine the magnitude and direction of the net torque exerted on the pulley. All right, can we find the magnitude and direction of net torque based off of what we know about the falling 0.1 kilogram block? Well, I think the toughest thing here is recognizing how to use this graph because it's linear distance with respect to the square of time for this object. And this does take a little bit of expertise in the subject, but it isn't something you haven't learned. There is an equation that comes to mind that relates the distance with respect to time squared, and that's this kinematic equation. I'm going to use y for distance. Y is equal to 1/2 at squared. This is one of the kinematic equations with constant acceleration. And the reason why I brought this up is because I recognize that if I divide both sides by t squared here, then I have the slope of my graph. I have distance over time squared. All right. So from here, obviously these cancel here, and if I go ahead and multiply both sides by 2 to get rid of this 1/2, then I have 2 times the slope of my graph is equal to linear acceleration of the box. And if we have linear acceleration of the box, then we can quickly get angular acceleration for the pulley if we go ahead and just multiply that, or just set that equal to r times alpha. All right, that's the relationship between linear acceleration and angular acceleration. So yeah, we have angular acceleration, and that's kind of huge because torque, the magnitude of torque can be calculated using moment of inertia times angular acceleration. And we already know that we know the rotational inertia, the moment of inertia. So if we can go ahead and calculate using this graph our angular acceleration in the manner you see here, multiply that by the known rotational inertia, then we have the magnitude of torque. And we don't need anything else. That's everything right there, because if we just look at figure 1, we can see that it's going to be rotating in the clockwise direction. So yes, the student is correct in saying that we can find the magnitude and direction of our torque. Now, for our answer choices, it looks like C and D say that the student is not correct. So I'm going to go ahead and mark those out. For A and B, we have that for A, it says the student is correct because the linear acceleration of the 0.1 kilogram object can be determined from the graph. Yeah, that's true. The angular acceleration of the pulley can be determined. That's correct. The direction of the net torque will be in the direction of the angular acceleration. That's also correct. All right, so I'm going to go ahead and circle A, but I'm going to read B just to make sure that I'm not crazy. The student is correct because the average linear velocity of the 0.1 kilogram object can be determined from the graph. The average angular velocity of the pulley can then be determined. The direction of the net torque will be in the direction of the average angular velocity. That's actually not necessarily true. So we're going to go ahead and sit with A and move on. All right, so here we have a question with no figure. In an experiment, a solid uniform sphere is at rest on a horizontal surface. A net force is applied tangentially to the edge of the sphere, so basically at a full distance of the sphere's radius from its axis of rotation. That is the greatest horizontal distance away, exactly what I just explained. The sphere begins to rotate from rest until the force is no longer applied after 3 seconds. Frictional forces between the sphere and the horizontal surface are considered to be negligible. Which two of the following quantities, when used together, could a student measure to determine the change in angular momentum of the sphere from 0 to 3 seconds? All right, so we're looking for change in angular momentum. And so we know time. We don't know pretty much anything else there. Let's see. we can go ahead and write the torque impulse relation to start informing us what we need. We know time. So all we need are two things that will help us find torque based off of what we know. All right. So we can go two ways with this. We can use Newton's second law, suggesting that we need moment of inertia and acceleration, or we can go the route where if we knew the actual applied net force, we would just need the radius of the sphere, F times R. All right, because we know the force is applied tangentially, so if we just know that force and we know the radius of the sphere, then we can find torque, because of course torque is equal to Fr. Let me see. Average net force exerted on the sphere, yeah, D would do it for us as long as we also had the radius. That's all we need here.
With this problem, we have a system that consists of a horizontal rod and two small objects shown here as these black little dots. The horizontal rod has a total length of 2L naught and a mass of capital M, with rotational inertia equal to mL squared over R. Each object has a mass, each one of the little black dot objects has a mass of m naught, and I suppose we're going to treat them as point masses because we're going to use a moment of inertia as mr squared. R is, of course, the distance of that specific object from the axis of rotation. The objects are fixed to the rod at the positions shown in the figure. The system is initially at rest, and a net torque is exerted on the system until it rotates with an angular speed omega naught about the vertical axis shown, which is through the center of the rod. What is the change in angular momentum of the system from when the system was at rest to the instant when the net torque is no longer applied? Now, since the system starts from rest, the change in angular momentum of the system is equal to the final angular momentum of the system. So, if we, let's say we have the sum of all momentums here, all right? So let's say we're trying to find the angular momentum of the rod plus the angular momentum of the object. Let's see, object 1 plus angular momentum object 2. The final angular momentum of the system is just going to be the sum of all of our final angular momentums. And we can actually calculate the angular momentums here symbolically, because as long as we know the definition for angular momentum, it's just I omega. Okay? It's just I omega. Then we can go ahead and just plug in everything we know, because we know all the I's, and we know they're all going to be traveling at the same omega. All right? So, that said, we can say that L final is equal to, for the rod, it's going to be moment of inertia, which is m L naught squared over 3 omega naught, plus for the first object, it will be, if I say the first object is this object, then the L is going to, or their R is going to be equal to L, because it's exactly 1 L away from the axis of rotation. So we'll go ahead and say plus m naught L squared, that's the moment of inertia, times omega naught. And then we're going to have plus one more thing. That's going to be this dot, which is of radius 3L over 5 away from the axis of rotation. So then I'm going to say m naught 3, and then in parentheses 3L naught over 5. Sorry if I write into the words here. All right, this is going to be squared times omega naught. So that's just each momentum. So this one is the rod, this one is the dot on the left, this one is the dot on the right. From here, we'll have to just do a bit of simplifying, kind of putting things together and factoring out omega. So what I'm going to be left with here, if I kind of put all these together and factor out omega, is something like this. In parentheses here, we'll have, of course, the m, capital M, L naught squared over 3 plus, and then I'm going to put the two objects together and factor out an m from them, just to make it all something that we can kind of simplify how much we're writing here. So I'm going to say m naught 34 L naught squared over 25. And then this is all times omega naught. All right. So the exercise here, and I think the tricky part here is how the algebra here comes from here to here. So work on that. If you have any questions specifically, go ahead and ask in the comments or ask me specifically. But we do have an answer choice that resembles this. It's answer choice D.